Hi, this is Scott Wilkinson, host of Home Theater Geeks. In episode 129, I chat with Derek Smith, the co-founder and CTO of Spectracal, about their new color calibration technology. Coming up next.
Netcasts you love.
From people you trust. This is TWiT.
Bandwidth for Home Theater Geeks is provided by Cachefly at CACHEFLY.com.
This is Home Theater Geeks with Scott Wilkinson, recorded September 24th, 2012. Episode 129, Color Cube Calibration. This episode of Home Theater Geeks is brought to you by Netflix. Watch thousands of TV episodes and movies on your PC, Mac, iPad, iPhone, or TV instantly. All streamed directly to you, saving you time, money, and hassle. For your free 30-day trial, go to netflix.com/twit. Hey there, Scott Wilkinson here, the Home Theater Geek. This week's guest geek is Derek Smith, the co-founder and CTO of Spectracal, who's going to be talking with us about a new calibration technology that his company has developed. So watch out. We're going to get super geeky today. Hey, Derek, welcome back to the show.
Thank you, Scott. I always appreciate being interviewed by you a number of times, being able to talk about new technologies the company's working on, new paradigms, and new milestones that have been happening in the calibration industry.
And there have been quite a few. Before we get to them, though, I know you're going to give us a little summary of how calibration has developed over the years. Before you do, I want to make sure that those who are watching live at live.twit.tv or logged into the chat room at irc.twit.tv can post questions for Derek as we go. I'll be watching the chat room, and I'll pass along as many as I can. So we're talking about TV calibration here, TVs and projectors. And I know you wanted to start with a little bit of a history of calibration. So how has it progressed over the years?
If we go back to more than 10 to 15 years ago, where televisions were primarily CRTs, there wasn't much to adjust or calibrate. If everybody kind of remembers the SMPTE patterns that we've seen late at night with the color bars that went across the screen, there were a couple of things we could do with those. We could set brightness, contrast, color tint, and maybe sharpness. That's about all we could have done with our consumer CRTs back in those days. And then about 10 years ago, when the manufacturers started switching over to digital processing, even though they were still CRTs, they had the ability to be able to manipulate the signal beyond the normal characteristics that a CRT provided. And in doing so, they started providing some internal calibration capabilities for us, typically in service menus. But if people were adventurous enough to go into a service menu, they could start adjusting their white balance, basically the color of white on their TVs, to compensate for the aging phosphors on their television. So red would age at a different rate, and so the TV would become red deficient. They could start calibrating those. As more and more digital technology TVs started coming out, flat panels, LCD, plasma, and now LED, in the digital world, the manufacturers can do anything they want. There is no natural calibration. There is no natural colors. There is no natural gamma. And so what we found is the manufacturers started getting very, very creative in how they started presenting these displays to consumers. And so they started providing the ability to adjust white balance at two places, 30 and 80. And then a couple of years after that, they started providing the ability to do white balance at a number of places, usually 10% steps, so 10%, 20%, 30%, up to 100, which also allowed us to then start taking gamma, or the natural fit of when, how much energy comes in versus how much energy comes out on a display, to start mimicking how CRTs worked. And then about 5 years ago, the manufacturers started coming out with what we call color management systems. And the reason they had to do that is they found that TVs that were brighter and more colorful sold on the television, on the showroom floors. But as we know, a TV that has a much brighter green or a more greener green isn't naturally the correct choices. When television producers are looking at material, or directors, they're making subjective choices on what color green should be and all the other colors. And if a TV is producing a different color, then it doesn't look natural, even though it's brighter, it looks more colorful. So they started coming out. Sorry, go ahead, Scott.
Sorry. Let me interrupt you for a second here. Really, what we're talking about is reproducing the director or the producer's intent as much as accurately as possible, right?
Yes, that is correct. And so what happened was the manufacturers of content, whether it's producers, directors, whatever, are typically looking at a calibrated display in a room that has specific type of lighting. They're typically, they traditionally have been, even up to just even today, Sony CRT monitors. They have a very specific look. And so they were making all their color choices, subjective choices on that. And now that we have digital technologies, the manufacturers can do anything they want in a display, including completely deviate from how a traditional CRT looked. And they started doing that. They started providing TVs that were really, really bright and very, very colorful. But if you look at a TV that has an what we call overly saturated green, and you try to look at what should have been a natural scene that the director was making choices of, your grasses are going to look neon green, your skies are going to look artificially blue. You just get these kind of cartoonish looking colors out of it. So the manufacturers
I'm sorry, I have a question for you. So when you finish your thought, let me ask. Go ahead.
Okay, so I was saying is the manufacturers then gave us what they call color management controls, the ability to calibrate the display or rein in those oversaturated colors back to where they were supposed to be.
Okay, now you said earlier, and I wanted to follow up a couple of points you made a moment ago, one of which was that these TVs, the digital TVs, the new flat panels and LCDs and LEDs and plasmas and so on, didn't have a native color, but they do, don't they? I mean, plasmas still work on phosphors, and those phosphors emit a certain color of red, green, and blue. LCD TVs have filters, red, green, and blue filters, which have a native color to them. And some of these TVs actually have, when you can choose a color gamut, which is the range of colors they can produce, they have a setting called native. And so this actually causes a problem with calibration when you're trying to change the colors that a TV produces. You need to the instrument that you're using to measure has to know what the native colors are, which aren't the same between one device and another. Have I got that right?
Yes, that is also part of the technologies. And so when you're measuring a display device, we have to take into consideration what we call the spectral display response, or the SPD. And we look at how the TV is actually producing colors. And so as you pointed out, we had CRT, which was a known SPD that everybody's been working with. And then they came out with LCDs, which use a CCFL type backlight. And they were able to get the CCFLs to mimic fairly close to what the CRTs were, because, again, they're also phosphor-based. And then the plasma TVs, again, are phosphor-based. So they were able to get fairly close to the CRT. And then they started coming out with LED displays, which are very, very narrow band lights that they tried to mimic how a CRT works. But they found in doing so, they could make the colors even more saturated beyond what CRT or any other phosphor-based device was capable of. And as a result of that, the LED manufacturers, LED backlight manufacturers of LCD TVs started creating very, very overly saturated, very large gamut displays. The plasma manufacturers had to do the same thing to keep up. The projector manufacturers had to do the same thing to keep up by providing filters that were a much, much wider gamut. And it just aspirated the problem by trying to create wider gamuts than what was originally intended.
Right. Right. Lawn Dog in the chat room is saying, sounds like we need a color standard for digital technology, digital displays. It's critical for the colors, no matter what format they're recorded in or displayed in, that they need to be the same as what the director intended. And that's really what we're talking about here is no matter what there is a standard for what the red, green, and blue should be, and presumably the director and the content creators are looking at images that conform to that standard. And now what we want to do is make sure that the display device in the consumer's home also conforms to that standard so that everybody is seeing essentially the same thing.
Yes, that is correct. The standards that we're working with today are called D65 Rec 709, and those define what our white balance is and what our natural gamut of the display should be once they're calibrated. And those are standards that have been adopted pretty much worldwide. And so we've got the ITU out of Europe, we've got the EBU out of France, We've got the SMPTE out of the U.S. They pretty much all agreed that Rec 709 D65 is the standard that all the materials should be mastered to and against. And the content producers are, in fact, looking at displays that have been calibrated to those standards. Luckily today, the manufacturers of consumer displays have given us enough calibration control within the display. So no matter what subjective choices they make or what they think they need to do to sell TVs, once they're in the homes and we have the right equipment, we can actually calibrate those back to the standards that were originally intended for the material.
And that's really what Spectracal is all about, right? I mean, you make software and you also market or sell hardware, instruments that allow people, professional calibrators as well as enthusiast consumers, to do exactly that, to get their TV to conform to those standards, which they certainly don't when they come out of the box.
Yes, we sell consumer calibration packages, for as little as $150, up to $400 for the consumer market, and then additional for the color sensors that we brand or rebrand from X-Rite and other manufacturers, all the way up to the high-end packages that the Geek Squad from Best Buy use. They use our products for their services. A majority of the professional calibrators that are out there, whether they're ISF or THX certified, use our products for their calibration services as well. Just this spring, we started branching out into additional technologies beyond the consumer television space. And so we're working in the medical industry, in the high-end PC, graphics arts industries, display matching industries for video walls. We're finding that color calibration is much, much more beyond just the consumer space.
Sure. It's funny you mentioned video walls. I was at CEDIA a couple weeks ago, and on the way back in the airport, we had lunch at one of the restaurants, and they had a video wall. And one of the TVs was so far off of the display panes, I should say, the tiles, was so far off from the others. And all of us at lunch kind of looked over there and went, oh, man, they need to calibrate those things. So it's an important thing when you're talking about video walls, much less consumer displays at home when there's only a single image.
Yes, we were at NAB and Infocom this last spring in Las Vegas, and we found that is one of the prevalent problems with video walls now. And we're finding that video walls are starting to replace projection systems. So if you go back a number of years ago, you'd go to boardrooms or large areas. They were either rear projected or front projected with very large or very bright projectors. But those have very expensive run times, maintenance, and those type of things. And the manufacturers are starting to produce these video wall panels that are designed to be put together. They're very, very thin bezel. They run for a long period of time because they're typically LED backlight. And they can make up very, very large video walls. But as you pointed out, all it takes is for one of those two panels to be out of sync with the other, out of color with the other, and they really, really stand out. We essentially get the Skittles effect where each panel looks differently.
iPad 24/770 in the chat room is asking, since rooms vary in brightness, that is to say the ambient light, how does that affect the calibration?
That does take effect in the calibration. So, for instance, if you're watching a movie that has a lot of dark scenes, a lot of the ones that came out recently, for me, it started off with when we go back to Lord of the Rings and that whole trilogy series, they had a lot of really dark scenes. And I had a television in a fairly large room with white walls, and I was having trouble seeing a lot of the fine detail in those dark scenes. And what I found was if I had the lights on the room, I had to increase the overall light output or the brightness level of my TV to compete or over-compete with the ambient lighting in the room. And so often we have televisions now that have multiple calibration settings, and we often refer to them as either day and night or light and dark, depending on which standard they're developed to. And so we can calibrate a TV that's meant to be used more in the day. So you'd bring up all your levels, make the TV a bit brighter so it can compete with ambient lighting. But at night, when you turn all the lights down and you want to watch movies, you find that is too bright. And so we lower it down so we can compensate for it as well. And you get a much, much better picture out of then also compensating for your ambient room lighting.
Mm-hmm. Lawn Dog in the chat room is asking, or is remembering AFC, automatic fine tuning or fine calibration. And if you turned on that feature, sorry, go ahead.
Yeah, it was automatic contrast control or automatic brightness or lightness control.
Right.
A number of manufacturers started coming out with that. But the problem is, so if you think about it, if you look at a TV and they had one of these capabilities, and you look at where the sensor was. The sensor was looking out into the room at you, and you're looking at the TV back the other direction. And so it was a good idea. The problem was the sensor was in the wrong place. For that technology to work, that sensor actually should have been in your seating position, basically from where you are, looking back at the TV. So it took the TV into consideration and the back wall, but it wasn't. It was looking the wrong direction, so it was making the wrong choices. So it's not that the technology is wrong or bad. They just couldn't put the sensor on the other side of the room looking back at the TV.
Well, that makes total sense. And there are plenty of TVs today that claim to do that have a sensor of some sort that takes into account the ambient light in the room and makes automatic adjustments. But I haven't found that they work very well typically. I usually turn them off.
Typically, we recommend you turn them off. And again, it's for the reason that the sensor's just in the wrong place. I mean, the algorithms are there. I've played with technologies that work. We know we can automate those type of systems. But again, the sensor's just looking the wrong direction.
Right. Well, let's get now to we took a little bit of a diversion here, so let's get back to the main topic, which is you were talking about how you can calibrate. We came to the point where we could calibrate the grayscale, that is the color of gray or the color of white, all the way from black to white. And in the early days, you could only do it. Well, and most cases today, even you can only do it at two brightness levels, and typically we do it at 30% of full white and 80% of full white. That's called 2-point calibration. Some TVs now offer a 10-point calibration in which you can do it at 10% increments from black to white. And then we got a color management system, which let us actually move the colors around. And before we get into color cube calibration, which is what the new technology is, I want to ask you about why is it that CMSs, color management systems, so often make the picture look worse than if you did nothing at all in terms of the color. I've found that to be true. In some cases, they do improve the color rendering of the image, but in many cases, it just looks horrible.
Part of the problem that the manufacturers had to come up with is if they're creating a gamut that's much bigger than what the manufacturer intended, so our reds are much more red, our blues are more blue, and our greens are more green, what happens is if they just try to run program material through that, flesh tones will look wrong. And so they do these creative things. So they can run a very, very bright red, but flesh tones are slightly in from red and slightly up towards yellow. And the manufacturers do creative work in that area. So they will naturally desaturate that very small part or that area of the color gamut so flesh tones look more natural on their overly saturated displays. So then we take a display that's overly saturated and we reduce its saturation down to where it should be, to the standards. But what happened to that flesh tone area that the manufacturer thought they were being creative about fixing? That just got moved in as well. And so now flesh tones don't look right. And so we were able to fix all the other colors, but flesh tones are still wrong. And so they came up with a tradition, what we're calling creative color decoders or flesh tone decoders. They just came up with something that fixed one problem but created another problem. And so that's often why CMS systems look right in certain areas and break other areas completely. The technology over the last couple of years, or kind of the accepted standard, was instead of measuring at 100% saturation, we started measuring at like 75 or 80% saturations, which is more of where those flesh tones start to line up. And so we tried to compensate for it, but it was never perfect because the manufacturers made subjective choices on how to fix their overly saturated displays.
And just before we go any further, remind us again why TVs, and this has been asked in the chat room a couple times, why TVs don't come out of the box adhering to the Rec 709 standard.
The manufacturers have been getting better about providing a cinema mode or a theater mode or these various preset modes from the TVs. So the last couple of years, they've known that if they provide a TV that's overly saturated, overly bright, has issues with color decoders, they at least have one mode that gets it close. But what we found is we've talked to a lot of display manufacturers, their whole goal is to produce a TV and get it out the door. It spends between 5 and 15 seconds being set up and calibrated at the factory. And so they don't have time for a lot of adjustments, a lot of testing, and a lot of fixing of those. There are a couple of manufacturers of high-end systems that are starting to provide TVs that are pre-calibrated or even better calibrated at the factory, but those take anywhere from 2 minutes to 10 minutes to properly calibrate. And the consumer displays, they just don't have time to do that at the factories.
What about THX certified displays? I've found that the THX mode, which is supposed to adhere to these standards, gets reasonably close, but you could get even closer with a full-on calibration.
The THX modes are great, but one thing that they don't take into consideration, and this is what we were talking about earlier, is your room lighting. You know, your dominant room color. Do you have a room that's got red walls and red furniture, or white or black? Do you have a lot of lighting? Do you have tungsten lights? Do you have LED lights? Do you have natural light? And so they're not able to account for that or compensate for that. But at least in THX mode, it is supposed to turn off all the creative stuff the manufacturer did, reduce the color gamut more closer to standards. And so, yeah, either THX mode, cinema mode, theater mode, any of those modes that disable or minimize the manufacturer's creative choices are the best thing out of the box.
That's certainly what I've found. Okay, so now we come to the present day. We've covered the history up to this point, and Spectracal has just announced and released in their latest version of your software, which is called CalMan, a new type of color management system that provides a much greater degree of control. Tell us about that.
Well, to call it a new system isn't quite right, because this system's actually existed for about 6 years in the professional high-end space. And so what we found was when we started building CalMan 5, we started working on it about 2 years ago, and we knew that we wanted to grow beyond the consumer space. We started looking at other industries like I was talking about in professional broadcast and studio and medical and PC, high-end PC systems. We found when we went into the studio space, the guys that are in the broadcast studios, the guys that are making the subjective choices on how colors should look, they often have what are called lookup tables or LUT boxes or LUT processors in their video stream. And the purpose of this box can be one of three things. It can either be a color space conversion, converting from one color space to another. It can be a creative color choice. They want everything to have a kind of a green overcast or overly saturated colors. That was their subjective or creative choice. Or it could also be used for corrective. They're trying to fix a display that had overly saturated or poor gamma curves. And so for about 6 years, they've had these high-end boxes. These boxes were, $5,000 to $10,000 just to stick in your video chain. And so this technology has existed for these high-end systems. What has changed today is there's now hardware that's available in the consumer space, and I'll talk about that in a little bit, that is capable of bringing that technology into consumers' homes. And so we felt the work that we were doing on CalMan for studios would also benefit in the CalMan for home theaters. And so the color cube or the 3D cube space has been around for a while, but it just hasn't been affordable or practical to bring into the home space. And since we'd already done all of that work for the studio version of CalMan, to bring it into the home theater version of CalMan, we already had the code there to do it.
So that made it relatively easy, as long as you could depend on having the hardware that would support it. Yes.
And so all of this correction is based on hardware. So CalMan does all the measurements via colorimeters or spectroradiometers. It puts up test patterns, but then it has to do something with all that data. And being able to correct a box, we need to be able to talk to hardware to be able to do that. And so the first consumer device that just came out, in fact, this has been out for a while, the Radiance processor from Lumagen has been out for a number of years. It's a great video processor. It's regarded as, basically the cream of the crop for the consumer space. We met with Jim Peterson at CES this last year in 2012, and we said, we're working on the studio version of CalMan, and we're going to be talking to these very, very high-end LUT processor boxes that are $5,000 to $10,000. Wouldn't it be great if you could add even a piece of that back in your Radiance processor for the consumer space? And so we talked with Jim Peterson on and off for the last 6 to 9 months, and just announced a couple of weeks ago that he's been working on that technology in the Radiance, And we've been working on support within CalMan for the Radiance as well. And we announced kind of the co-partnership at CEDIA this year that we had CalMan being able to calibrate the Radiance in a 3D cube space, and the Radiance had all the hardware capability. So now the consumers truly do have the ability for calibrating their displays to the same technologies that are used in production studios.
Now, how much is the Radiance processor?
There's 3 versions of it, and I believe it's $2,000 for the what they call the Mini. It's 2 inputs, 1 output, and then they've got their SX, their XD, and XE, and so it's anywhere from $2,000 to I believe about $5,000. But it's a processor. It's just not a switcher. So it does processing, switching, scaling, calibration. They have the ability to hook up 3D emitters, so you can do 3D stereoscopic interfaces as well. So it takes it much, much beyond just a LUT box like what's normally used in a studio space. You just get the benefit of all that other capability when we turn on the 3D LUT calibration.
And so what happens is, I guess what happens is you've got your source device, say a Blu-ray player or a TV tuner, a satellite receiver or whatever, cable box. That goes into this Radiance, Lumagen Radiance processor, and then that goes on to your TV. And the Lumagen, the Radiance processor, manipulates the color according to CalMan and so on, and sends that information to the TV. How does the TV then respond to that to change its colors?
So basically what happens is within the calibration interface of the Radiance, we're actually changing the values from when they go into the Radiance to when they come out of the Radiance. So the TV doesn't actually know anything's happening. The TV thinks it's just getting a regular signal, but those values from input to output on the Radiance have actually been manipulated or changed to go into the TV. So the TV, it doesn't really matter. We usually recommend that you pre-calibrate or pre-set up your TV. You set brightness and contrast, try to maximize the dynamic range. Select a color, temperature, and a gamma within the TV that are reasonable, but it doesn't take much to get the TV to a place where then the Radiance can do all the correction.
Okay. We've been using this term gamma, and I want to make sure everybody understands that. Can you explain it to us in relatively simple terms?
Sure. Basically, the idea is when we have a television camera and that inputs light into it, that light isn't in linear. And so, for instance, if you have a 10% light output, or excuse me, 10% light input to 100% light input and 50% light input, those are not on a linear graph. They've actually got a natural curve that comes in. We call it a gamma curve. And so when it comes to the TV has to do the opposite of that. And so it basically has to de-gamma the gamma curve that came from the television cameras so that we get a linear response out of the display. And what's happened today is, all the cameras are digital now, just like they were, and the displays are digital. But there's been so much material that's been produced from CRT cameras that they've just naturally adopted the gamma curve for all digital devices as well. If when we went to digital devices and digital cameras, they decided to abandon all the gamma curves and just did a one-to-one linear response, they could have done that, but they would have been abandoning 50 years of material, and so they had to have backwards compatibility. And so essentially, the gamma is. I'm sorry. Go ahead. No, I was saying, so essentially, the gamma is a corrective response to what we're getting from the cameras.
Right. I was going to say that as you said, we would be if we abandoned gamma, we would be abandoning all the material that was made for the last really almost 100 years, with certainly the last 50 years with television cameras, and they wouldn't look right if you played them on a TV that did not have a gamma. So we have to stick with that at least in the foreseeable future, I would say.
I don't see it changing. They've adopted these standards for backwards compatibility. There are industries, the medical industry that we've got a product for, has their own gamma standard. It's actually a linear response, and it's called J&D, just noticeable differences. So each step you go up in the digital pyramid or the digital stepping that you go up, each of those steps have to be visually discernible from each point. And so it's got a natural response that's closer to linear for that particular industry. And so the displays are more than capable of it. It's just that we have to support backwards material for backwards compatibility.
Right, exactly. Well, let's get deeper into this 3D color cube calibration. But before we do, I do want to take a moment to thank our sponsor for this episode, which is Netflix. Of course, Netflix offers you thousands of TV episodes and movies that you can stream directly to just about any consumer electronics device you can imagine. TVs, Blu-ray players, game consoles, iPhones, smartphones, tablets, and, of course, computers. Just about anything that you have that has a chip in it will have a Netflix app that will let you stream it and stream it to a small screen or your big screen, anything you want, as much as you want for one low price, one low monthly subscription fee, which is actually the way I prefer it, to tell you the truth, rather than buying each program separately. You can even start on one device and finish on another. So you start in the living room and then you decide, I want to start crashing, I'll go to bed, but I want to finish this. So it'll easily transfer over to the bedroom TV or wherever you want to be. So it's the ultimate in convenience, and it just provides you with unlimited amount of content. I can't imagine anybody getting through all of it. You can give it a try, though. You can try for 30 days free. Just go to netflix.com/twit for your free 30-day trial. That's netflix.com/twit. And we thank Netflix very much for their support of Home Theater Geeks and the entire TWiT network. So, Derek, tell us a little bit more about then this color cube calibration, which is, I think, the way you're referring to it, right?
Yeah, I mean, technically, if we go to the studio space, they've been referring to it as 3D LUT calibrations. But we found as soon as we put the word 3D in front of anything, people often think the stereoscopic 3D, which this is not. And so we started talking about cube calibrations or cube LUTs, which is essentially, everything fits inside of a cube that's got 6 sides and 3 axes. And so we started referring to it as a cube more than 3D because we thought 3D was confusing.
I have to tell you, I thought it was confusing myself. At CEDIA, I talked with your colleague, L.A. Haberlein, and he mentioned 3D calibration. I said, oh, you mean for 3D displays? He went, no! So I think you're very smart to refer to it as something else, or as you are, a cube, which is also a three-dimensional thing. We have a couple of graphics to show here. Let's take a look at the first one that's a color cube with the axes X, Y, and Z, or red, green, and blue marked. There it is. Tell us what we're looking at here.
Well, essentially, this is a color cube. And so if we look at our color in a three-dimensional space instead of the traditional flat two-dimensional space, color has hue, its natural color. It has saturation, how bright or how dim the actual color is. And then it's also got a brightness or lightness, how dark or how white it is. And so in order to represent color in a three-dimensional space, it has to be processed in a three-dimensional space as well. And essentially, this diagram shows that in the center is where our white is, and if we come behind that center and we go backwards, if we rotated this cube, then we would go to black. And if we rotated the cube to any one corner, we would see the fully saturated red, blue, green, cyan, magenta, yellow.
Got it. Unfortunately, we can't see the axes. I can't very well on this image, but yeah, your white point is in the corner that's closest to us, and then as you go backwards, you get into the colors. We also have a screenshot, I think, from CalMan that shows a similar thing in the screen of CalMan. If we can pull that up, maybe we can't. There it is.
Okay, so on the right-hand side, we're looking at our traditional CIE chart that's a flat view of a 3D world. And so we see our natural gamma points. We start at the upper left-hand corner. We've got green, and then we work around our wave, green, cyan, blue, magenta, red, yellow, and in the center is white. But what that doesn't show us is all of the colors in between and all the colors in the third dimension, and so in the lightness or brightness dimension. The diagram on the left is actually that same thing, but in a three-dimensional space. And so we can see there's a lot more information that we typically haven't measured before, we haven't looked at before, that's truly in the three-dimensional space.
It would take a little getting used to, it looks to me, to look at that and sort of grok what's going on there. But this is a new technology for many of us, some of us not. those of us in the consumer space really haven't gone there yet. I certainly look forward to exploring it myself when I get CalMan 5 up and running and get a Radiance in here to play around with. So take us through the process. How do you actually go about using this new approach? Or it's not so new, but new to us.
So unlike our previous methods of calibrating before, where we could actually pick up a television remote and be able to go and change a few controls. So when we were doing 30/80, we had red, blue, and green at one level and red, blue, and green at another level. So we had 6 controls. And then we started doing multi-point gamma grayscale. And so we had 33 controls. That wasn't too bad. And then we started doing CMS systems or advanced CMS systems, and those had 18 controls for all 6 axes in 3 colors. So that wasn't too bad. So you could typically, if it wasn't automated or you didn't have a control interface, you could just pick up the remote and start changing values as CalMan was reading in them and showing you relatively in the chart where they were. With cube calibrations, the point count is much higher. So for instance, on the Radiance, the point count is 125 measurement and adjustment points. And on some of the bigger LUT boxes, like the Davio that we support in the studio space, that's got over 200,000 adjustment and measurement points. So it's not practical anymore. Even though we show you those diagrams, like the one that was on the left, where we showed you the color cube and where all the points are and where they should line up, that isn't a practical interface for calibrating anymore. There's not enough hours in the day to be able to try and move everything around. So the only way to truly calibrate a cube in a 3D space is through automation, because there's just so much that has to go on, and the algorithms are fairly advanced. And so, for instance, on the Radiance, it's got 125 points of measurement and adjustment. And so we measure the outside, and then we measure the inside, and we basically just spiral our way down through the cube as we're measuring points and adjusting it. That whole process takes anywhere from 20 minutes to an hour, depending on how much correction has to go into the display. And we're doing, tens of thousands of measurements and adjustments in that period of time. I mean, it's just iterative until we get it right. And so this is the first time that we've come out with the calibration technology that the only way to truly do it is through automation. The other technologies, even though automation was nice and it could speed it up, you could still do it manually. But with the cubes, it has to be the only way you can practically do it is through automation.
When you talk about when you talk about spiraling down, you're really talking about going from the brightest to the dimmest. Am I correct?
Yes, we start from the bright at the very top, and then we come down through the center, and then as we come down through each layer, then we measure the outside, then we measure the next layer in, and then we drop the next brightness level. We measure around the outside, we measure the next layer in, and we down to the next brightness level. And so basically, we're methodically measuring all of those 125 points as they intersect through the cube.
Mm-hmm. I had on the show some time ago Kevin Miller, a calibrator I'm sure you know.
Yes.
And he had conducted a flat panel shootout at Value Electronics in Scarsdale, New York. And he mentioned something interesting that relates to this, which is that on the, I believe it was the Sony 929, which is their top of the line LED backlit LCD TV, that the color cyan in particular did not track well as you changed the brightness of cyan. And I'm wondering if you do this through the Radiance, you probably wouldn't have that problem, would you?
That is correct. Basically, what happens is when we start looking at color correction in a three-dimensional space inside these color cubes that we work in, we can correct all the levels of cyan in their brightness level and their saturation level, and we do that for all the colors. So, red, blue, green, cyan, magenta, yellow. We're doing correction for all those, but we're also doing corrections between all of those points as well, so that we get into the very, very fine detail. So the problem that we were talking before about what we're kind of calling the one-dimensional color management systems, where we adjusted the outside, brought it in so it corrected it, but we weren't taking into consideration the area that the manufacturers had to deal with flesh tones. With this, that does, because we're looking at all the points independently. And so we can adjust the outside gamut into where it should be for the natural, or, you know, for the standards. And then we go in one level slightly from that, and we adjust that. And then we go in one level from that, and we adjust that. And so we're actually correcting for all the deficiencies the manufacturers have in their color decoders, or we're correcting out all the creative things that they did in their color decoders as well.
SoCal Ray Jr. in the chat room is correcting me. It was not the Sony 929. It was the Sharp Elite LED LCD, which Sharp bought the name Elite, or leased it, or somehow licensed it from Pioneer, and made an LED TV that had that cyan problem. It wasn't the Sony, and I apologize to Sony for making that mistake. It's the Sharp Elite. But either way, I mean, if you're going to buy a TV like the Sharp Elite, or the Sony for that matter, although the Sharp's a lot more expensive, it behooves you probably to spend another couple grand on an external processor if you want to get it just right. But if you're going to spend $1,000 or $1,500 on a TV, it's probably not necessarily worth it to spend more than the TV itself on the processor. How close do TVs get these days without doing this color cube calibration?
Well, we can measure TVs in a number of different ways. We can measure their performance on a gamma and grayscale. We can measure their performance in chromaticity. And then in CalMan 5, we just added a new capability for measuring color checker or color swatches, which have been used in print and photography for a long time. You know, Greetag Macbeth, Pantone, RIT, Munsell, these guys came up with 24 patches that basically evaluate how a display is performing, or cameras, or printers. And so they come up with a couple of different flesh tones, a couple of different greens, a couple of different blues at various saturation levels and lightness levels. And what we're finding is when we measure displays out of the box using our color checker chart, we're seeing displays that have a delta error of over 10, which are visible errors. If we take that same display and we use the traditional CMS calibration method, where we just bring the gamut in and we fix the outside edges, but we're not correcting for the color decoder issues or the saturations internally, in some cases we've actually seen the error go higher. We make the TV worse than doing nothing. As you were pointing out, some CMS systems, even though they're doing what they're supposed to be doing, can make the TV look poor. Even though they measure correctly and our charts looks great, the TV response doesn't look right. Because we just moved things around to where the manufacturers didn't expect those to happen. And then if we calibrate a TV to a 3D space, our 3D cubes, we're finding that we usually get a delta error of less than 1 across all these 24 patches. And so it can make a big difference. And we're finding some televisions that are even the medium-priced ones, where you spend $1,500 to $2,500 on a display, and the display fundamentally has really, really great capability, but the manufacturers chose to be very creative in how they implemented their color decoders and their gammas. And so even those TVs can respond well to external processing, even if you're spending about the same amount on processing as what the TV was capable of. We're finding you can get a lot of performance out of these medium-priced TVs now as well.
I should also point out, just for people who might not know, that the delta error that you're referring to is a way of quantifying how correct, how accurate or not a particular color is. And I know that in black to white, in the grayscale, a delta error of 3 or less is generally considered to be indistinguishable to the human eye from being perfectly correct. Is that same delta error applicable to color as well? If a delta error is less than 3 in red or green or blue or one of the secondaries, is that also considered to be kind of the cutoff point to indistinguishability?
Yeah, we've kind of adopted, I mean, there is no industry standard for what delta error should be, but through measurements, trial and error, talking to a lot of industry experts, a delta error of 5 or less is acceptable. A delta of 3 or less should be indistinguishable. A delta error of 1 or less, you're starting to approach reference grade material or reference grade monitors. And so somewhere between 1 and 3, if you can certainly get to 1, which we're finding is a lot of cases even on these medium price displays, we're able to get under 1. You're as good as what they would see in a reference monitor in a studio.
Now, Lawn Dog in the chat room has been commenting here throughout a little bit about the similarity between chasing perfection with tweaking in a video display and doing the same thing in audio, which audiophiles have been doing for decades. And I don't know, how do you feel about that? Are they comparable, parallel types of efforts, or is there something fundamentally different between those two pursuits?
No, I agree about the pursuits. I mean, if you're an audiophile, videophile, just an enthusiast, that you want to get the most out of what your equipment's capable of, no matter what you purchased or brand or its capabilities. You want to get the best performance out of it. My background has typically been audio. I go back into the late 70s, early 80s, and 90s designing amps, speakers, crossovers, calibrating two speaker systems, and then we became multi-speaker systems. I built a home theater in early 2000, designed my own speakers, amps, crossovers, set up the room acoustically, and then started putting in video and realized that my video system didn't even come close to matching the audio. And so that's where my pursuit down the video path came down. There are a lot of parallels. If you look at audio systems going back 5 to 10 years ago, some of them had calibration capability, or you just pulled out your own audio meter or your real-time analyzer and started adjusting the room and the capabilities within the audio processors. At some point, the manufacturers started providing home theaters in a box and giving you a simple microphone, which may have set up levels and distances and a little bit of basic EQ to try and correct for the room or speaker placement. Video is kind of going down the same path, where we can bring a panel, TV, projector, into a room and adjust or compensate for that room and then bring it back to standards through various measurements, whether we're talking to TV internally, externally, through an internal sensor, external sensor. So they're going down parallel paths. It's just audio is much further ahead, and audio is a much more complex problem. In video, we don't have to worry about light reflecting off the back wall and coming back at different rates because of different colors, unlike audio where we've got to have the sound delivery of 7 speakers arriving at the same time at all various frequencies. We don't have those complexities in video. So I think the problem is actually easier in video, but for an enthusiast, the goal is still perfection out of the equipment that you own.
The other difference that I see between them is that video has a very clear standard. You have the Rec 709 color gamut. You have the gamma that people will argue about, but there are certain numbers that are generally accepted as being correct. You have the color of gray that is either right or it's not, or it's within a certain delta error. With audio, what is the similar standard other than saying I want it to be flat, which isn't necessarily the best thing to do?
No, that is true. In fact, I was just talking to a friend about this the other day because I've also got an audio studio at my house for mixing and editing music and other stuff as well. And the goal typically is to have a room that's flat, the speaker delay and delivery all arrive at the same time to the seating position. And then I asked him, it's like, when was the last time you went to the audiologist and had your hearing measured? And he says, well, it was last year. And I said, did you get a chart from the audiologist to see what your hearing response is now that we're getting older and we're starting to tail off the top end? He goes, yeah. I says, are you calibrating your audio standards to that as well to compensate for your deficiencies in hearing? And he hadn't thought of it before. He's like, you're right. I just calibrated my room to an RTA so it's flat, but I don't hear sound flat anymore because of age. And so right. the audio stuff is way more complex than the video side of things as far as those regards.
Even youngsters don't hear flat. I mean, there's the Fletcher-Munson curve, the famous Fletcher-Munson curve, which demonstrates the response of the human hearing system. And even those that can hear out to, well, even teenagers probably can't hear to 20K anymore, but babies can. But even babies don't have a flat response to their hearing.
Yes, no, that's I agree. And I'm saying that was my passion. It goes back 20-some years. It still is today. I'm as much involved in the audio side of things as I am video. And they both have their own complexities. For me, video has been a challenge because I have a condition in my right eye that I'm slightly red deficient in my right eye, but not in my left. So I see reds differently than everybody else. And depending on what angle and what system I'm looking at, they look different as well. And so, I've had a challenge in some cases of you can't do it by eye because you don't know what your eyes are actually doing. And that's where the colorimeters, the spectroradiometers give us a subjective, or not a subjective, but an objective measurement of what's coming out of the display.
This is a very important point I want to reiterate and reinforce, because a lot of people, not calibrators, but end users might say, oh, I'll just make these adjustments to the CMS and the grayscale and everything. I'll just make those adjustments by eye, which I always say, don't do it. It's a bad idea. You want some objective measurements to get really where you need to be. The other thing you said was so interesting to me. You said that you have a little bit of a problem in one eye. It's a little red deficient. I wonder if, I've never seen this, but I wonder if it's possible to generate a spectral response chart for your eyes, much like an audiologist generates a spectral response curve for your ears.
That is very interesting. I haven't seen, well, I would imagine there's been research done on it, because when they come up with standards on, the transfer function from a spectral display response to a color matching function to produce the XYZ and the RGB values from these colorimeters, they are based on studies that have been being done over the last 60, 70 years. So they must have had some system to determine how we see color and light based on what our eye sees. But I actually haven't seen any of the equipment that's used. I've just read some of the studies.
Right. Now you've inspired me to go talk to my eye guy, my eye doctor, and see if there's any sort of chart that one can get to sort of objectively see what it is you're seeing, and if you're deficient in red, for example, or one of the other colors, or how you're responding to colors. That might affect how you calibrate a TV. Although, as I said before, we have a clear-cut standard that we should really all adhere to at this point.
Yes, I mean, they have, when you go to the eye doctor, they have the charts they use for detecting color blindness, but those are fairly, on or off. You either are or you aren't, or you have some level of it. Mine is actually very, very subtle into just one eye. And how they found that was through very, very expensive testing, shooting dyes into my eye, measuring the responses with high-resolution cameras.
Oh, my God.
And so, well, they wanted to make sure that it wasn't something else happening neurologically within my head, that it was actually something physical in my eye, that I didn't, have a brain tumor or something that was going on when I first started noticing this about 5 years ago. And they found it was just my eye is reacting that way. But yeah, they did a lot of very, very expensive systems to determine that that's what the problem was, which isn't practical for, the everyday person to go through.
I'm sure that's true. Although our engineer John has amazingly found exactly a spectral chart. Oh, okay. Well, this is the general. Now I understand what John found. This is, in fact, the spectral sensitivity to the three primary colors, red, green, and blue, which is, in fact, why we can recreate all of the colors that we see on a color TV with just three colors, red, green, and blue. And interestingly, the green is very close to red. It's not really separated by as much as you might think. What I'd love to see, now this is a sort of I think an average. What I would love to see is an individual one, like how does mine compare to yours, for example? I think that would be very fascinating, and I intend to look into that a little bit more. But thank you, John, for finding that. That's very good. That, in fact, shows us why we can recreate color TV with just three colors, red, green, and blue. Speaking of which, let me ask you this. We have a few minutes left. What do you think of Sharp's attempt to add a fourth color, yellow, into their red, green, and blue in what they called Quatron? You must remember George Takei's commercials for that when it first came out. Oh, my. What did you think of Sharp's attempt to add a fourth color to things?
We do have Sharp in here. They're one of our partners, so I have to kind of be careful on how I answer this.
All right.
Well, When we first heard or seen that Sharp was doing this, we went out to Best Buy and measured a number of different displays. We've got access to a number of local Best Buy facilities, so we can pretty much measure any display that comes up if we haven't gotten it from the manufacturers first. And what we found was the yellow color filters were helping to produce more light and a slightly bigger gamut, but they also used it to correct flesh tones. And so as we were talking earlier, the manufacturers started producing very, very wide gamuts, which they found on these TVs they could create a massively wide gamut, but then flesh tones weren't quite right. And so the yellow phosphors or filters were partially used to help correct flesh tones. JVC is actually doing this on their projectors. They've got an orange in their, if you look at their CMS correction, their CMS calibration capabilities, they've got traditional red, green, blue, cyan, magenta, yellow, but they've also got an orange. And it was the similar attempt, and they're using orange to help correct flesh tone areas as well. And so in I think manufacturers' attempt to give us wider gamuts, they had to come up with ways of correcting flesh tones.
But we don't want wider gamuts. We want the gamut that the stuff was made in, and the stuff that, you know, we want it to be, again, an accurate reflection of the director's intent, and what the director or the content creator was looking at was Rec 709. So I always object to when they say, oh, we want to look at how much wider our gamut is. Well, I don't want that.
Well, us enthusiasts, yes. We want things that are exactly to the standards that the director's intent, producer's intents are. But that doesn't sell TVs. If the manufacturers came out yesterday, you know, we picked a manufacturer, and their only marketing point was, we're producing TVs to the exact director's intent, they would probably not sell many TVs based on that marketing campaign. Now, if they came out and said, it produces more colors, it's brighter, it's more colorful, it's thinner, it's bigger, then that's what sells TVs. So we're always up against what sells TVs versus what we would like out of TVs. But thankfully, most of the major manufacturers have given us some capability to rein in their oversaturated colors. And then the ones that don't, we can use external processors to do that.
Mm-hmm. One last question. I've been getting some questions in the chat room about OLED and laser view, Mitsubishi in particular, although there are some other projectors now coming out with laser illumination. How do both of those technologies, laser illumination and OLED, I think they both promise wider color gamuts as well. Have you seen many of them? How have they performed?
I've seen a couple of different laser systems, laser hybrids, because laser projectors are actually going to start coming back. They're making a resurgence. And in fact, they're doing it in a unique way. They're actually using the laser for energy, but they're shooting it through a color wheel, like we did in the DLP days, to then get the proper color and wavelengths out of laser. Because you just can't shoot laser on a wall and have it come back with something that actually looks right. You get the speckling effect. You get really narrow band issues with it. And so they're actually going to be shooting lasers through color wheels to give us a much broader band, more natural looking color. And so we've been testing some of those. There was a couple of announcements at NEB and at CES and Infocom this last year about these new laser projectors. And then for OLED, there's actually 3 different OLED technologies that are being worked on that they're coming out with. The consumer-based ones that I believe it's Sharp and Sony, maybe it was LG, are talking about.
It was LG and Samsung, actually.
There we go. Okay, yeah. They're 2 different competing technologies, but what they did is, if we look at a traditional LCD, and we've got its backlight, which is typically a white light shooting through color filters that are turned on and off at a very high rate to give us, you know, essentially RGB, which then produces white on the other side of that. One OLED technology is all they're doing is taking the white LEDs and they're putting in white OLEDs instead, because they're brighter and they can be turned on and off much faster. So that's one type of OLED that we're going to see in the consumer space. The next type of OLED is where they're actually producing the OLEDs in RGB, but they're still going through filters to be able to then control the lightness level. So they get more finer control over grayscale and gamma, but it's produced with 3 different OLED backlights. And then the native backlight or the native OLED, which they're not going to be in the consumer space. These are all in commercial space. In fact, we just got one of the high-end Sony OLEDs in today. It's a 25-inch, and they're like $26,000 for a 25-inch OLED. Those are native light. And so basically, for every pixel, for every color in every pixel, it's actually got an OLED, and that OLED is turning on and off in a very, very fast rate for every single pixel. But again, those are very expensive to do. And so for the consumer space, they're doing either clustered RGBs or they're just doing native white. And so there's actually 3 OLED technologies out, and they all are capable of producing gamuts much, much wider than we actually need.
And so will they have, I've always said that I can't wait to have one to test and make sure that I can bring that gamut back into where it needs to be for current content. Can they do that?
I hope they do. I mean, within the TV's capabilities, they are, but hopefully the manufacturers give us enough control that we can. Because, more colors isn't necessarily better. The reason they're doing it in like the commercial panel that we got from Sony is they're using that same panel for television content as well as digital cinema. And also Adobe RGB, which have very, very large gamuts. And so they can have one TV or one display that's capable of switching in a very wide gamut from Adobe RGB or DCI, digital cinema, down to a narrow gamut that they have for broadcast or for commercial or consumer. So they have the ability of switching all these in and out. So in that case, it's a necessity that they have to have that capability in TVs. But for consumer TVs, they don't need all of that additional gamut.
Right. Well, all I'm hoping is that they give us the gamut that is what is used in commercial broadcasting and Blu-rays and stuff like that. I'm afraid we've run out of time. I thank you so much, Derek Smith, for being here and explaining color calibration, and what's new from Spectracal. I'm sure looking forward to trying it out as soon as I can. Thanks so much for being here.
All right. Thank you, Scott. I very much appreciate it.
You bet. Derek, of course, is at Spectracal, and you can find out all about the color cube calibration and everything else about CalMan and the Radiance processor and a variety of other goodies at spectracal.com. And you can email me at scott@twit.tv with questions that you might like answers to, guest suggestions, or just about anything else you'd care to communicate. Next week, my guest geek is scheduled to be Steve Venuti, who is the president of HDMI licensing. And we're going to learn all about what's new in HDMI. We now are at 1.4, although he will tell us that they're not using numbers anymore. So I definitely want to ask him about that. So I do hope you will join me for that, because it should be a fascinating hour. Until then, geek out.